So we will continue with the lecture on environmental forces. It is the second lecture on environmental forces. We are talking about the video program on advanced marine structures. In the last lecture we discussed about how the sea surface elevation as a spatial dependent and time dependent given by Airy's theory can be useful to explain the water particle kinematics. And unfortunate part is that the limitation is that this theory explains water particle kinematics only up to MSL, that is the mean sea level or still water level, but people have extended this for submergence effect. For example, I have got a cylindrical member, it may be fixed to the seabed, I have got a wave here and this is what we call as the crest of the wave, this is what we call as the trough of the wave. When the trough of the wave touches the body, then the force acting on the member is different. When the crest of the wave touches, the force acting on the different, this is what we call as submergence effect. In literature this is identified as stretching modification. People are given different stretching modification. In the last lecture we discussed about the modification suggested by Wheeler, and now we will discuss about the modification suggested by Chakravarti. So the horizontal water particle velocity and the horizontal water particle acceleration are modified based on Chakravarti's specification as the following equations. This is nothing but the derivative of this, it is acceleration. You can see here that eta, which is the sea surface elevation, is also accounted in the modification suggested by Chakravarti on the kinematics. So we will call this equation number 8 and 9. So one can say that the horizontal water particle velocity and acceleration are modified by including the wave elevation effect into the calculation, and of course as we saw in the last lecture, the water particle kinematics or the wave loading is function of two things. One is the space or spatial dependent, other is the time dependent. The one more aspect which depends on is y, where y is any point of interest where I want to compute my wave forces. So it is having spatial dependence both on two dimensional plane x as well as y, which is on the vertical. This is what the water depth is, small d, this is what I am indicating here, this is the diameter of the cylinder, and of course h is the wave height, omega is the frequency of the wave, and k is the wave number, and d of course is the water depth, and these are hyperbolic function, cos hyperbolic and sin hyperbolic. So there is no change in these functions except that the denominator of this argument has been now modified with the addition of eta to it. Now having said this, now if you want to really compute the wave force or the hydrodynamic force, on any marine structural member, one has got to actually identify the wave profile. So we already said in the beginning that waves are nothing but summation of n number of regular waves. This n can be finite number, n can be infinite number, which will have the summation of 3 components of a regular wave. I should say regular waves. The components are the wave amplitude can be different, the wave period can be different, and of course the wave direction can be different. If you put all of them together, then you will be able to really simulate a original wind driven open sea state to which a marine structure is exposed to. So I am trying to draw series of regular waves as you see in this picture here. I have taken 3 examples, 3 waves of different wave height, wave period and theta, but I am summing them up all, so I will get an irregular wave in every time. So let us say this is my, because I am trying to sum up different components here, getting an irregular wave. Maybe I have another record, What I do here is I pick up a timeline or timelines at equal intervals. Let the interval be tau. Now I find the mean square value of the record. These records are what we call as ensemble. I try to find the mean square value of these records. If this mean square value becomes unique across the ensemble, if it becomes unique across the entire ensemble, then I call this process as stationary process. The process becomes stationary. Now ergodic process is a special stationary process. Now what is the speciality in the stationary process which is identified as an ergodic process? Let us take a simple example. Now I am trying to measure the wave height. Wave height can be measured in open sea in many manner. Let us say I take a physical observation. Physical observation, a guess. I do this for let us say 365 days throughout the full 1 year. Every day at a specific time, morning 8 o'clock, I keep on observing the wave height, keep on recording it. I have 365 data with me. Now find the mean square value of this data. If this mean square value is exactly equal to the unique mean square value of the ensemble, then this process becomes ergodic. So shortly, ergodic is a single sample, it is not a set of records, it is a single sample which is arbitrarily chosen whose mean square value matches with the unique mean square value of the stationary process. Now interestingly, hydrodynamic force acting on the member will come from the waves. Waves are series and summation of regular number of waves of infinite number which has got different wave height, wave period and direction. Out of this complexity, I am able to pick up at random one specific signal which has got a mean square value, for example of the wave height, which is equal to the unique mean square value of the whole ensemble. Okay. Now I am considering only one wave or one signal instead of considering n number of signals. So I have now reduced the problem of considering n number of signals to one signal which is ergodic and a stationary process. Now the question comes, why are we interested in identifying a single ergodic process or a single sample? Because in short time period waves, the moment I say short time period, then I should define the period. It is typically 3 hours. So I take a wave record for 3 hours and try to use this process and pick up a sample. I call that as a short time period wave. Shows a zero mean process is ergodic and Gaussian. This has been shown in the literature. Now to understand why or what do you mean by ergodic, we are given this explanation. So I picked up a single sample which has got a mean square value which is more or less matching with the mean square value of the whole stationary process on an ensemble, and that is the data what I have with me, and generally that data has got a zero mean process and it is a Gaussian process. In such case, to find out the forces, people use John-Swap spectrum. Now John-Swap spectrum is further modified and people also use what we call Pearson-Moskowitz spectrum. We will talk about these spectrums now. So for a short time period waves in an open sea state, these spectrums are valid. When you talk about long period waves, in the long time period waves, that is the duration of the sample is more than 3 hours, the variations are slower. In comparison to the short term fluctuations, and people have seen that this becomes a non-zero mean process and it remains Gaussian and it cannot be ergodic. In such cases, two parameters are used to define the wave spectrum. One is the significant wave height, the other is wave peak period. So, for long period waves, people use these two parameters to define the wave spectrum. Okay. Now, the question comes, for a short period wave where Pearson-Moskowitz is applicable, do people require these two data to define the wave spectrum? The answer is partially yes, partially no, because there are modified versions of PM spectrum where people use Hs as one of the data. The original PM spectrum does not use Hs, it uses only one parameter, which is the frequency. Okay. So, we will talk both the spectrums now to understand, because once you know the spectrum, then you will know how to compute the forces from the spectrum. Before we speak about the spectrums or different spectra used for computing forces in marine structures, we will talk about what are the force components which act on marine structures. I should rather say main force components. There are 4 main force components. Frau-Krylov force, which actually originates from pressure effects due to undisturbed waves. In fact, I should say undisturbed incident waves. The second one is the diffraction force, which results from the pressure effects due to the presence of the structure in the wave field. It is called diffraction force. The third can be hydrodynamic added mass and potential damping force. They essentially come from the pressure effects due to the motion of the structure in the wave field. We consider the wave field as an ideal fluid, and therefore we say the aerodynamic added mass and the potential damping force are consequences of the pressure effects caused due to the motion of the structure in the ideal fluid. The fourth could be the viscous drag force, which is due to the pressure effects due to the relative velocity between water particle and the structure. So, this is very much true in case of compliant structures. So, these are main force components which act on a marine structural member. One is arising from the undisturbed wave, one is coming because of the structure interference with the wave, other is coming because of the motion of the structure in the wave, and other is because of the relative movement of the structure in the wave field. Now, interestingly, in the case of slender structures, the Freud-Kraloff force and the diffraction force together are idealized with a single inertia term. The moment I say the structure is slender, then I should say that the diameter of the member to the wavelength, then point. So, what is the advantage of having a structural system which qualifies this relationship? The advantage is, I have a structural system, it has got a member, do not worry about the boundary condition, we will talk about that slightly later. The member is slender, it means that the external diameter of the member with respect to its wavelength is less than 0.2. In such case, this is my axis of the member, you compute the force at any point on the circumference of the member at the axis line or anywhere here or anywhere here. There will not be much variation in the velocity and acceleration between these 3 points. Between these 3 points, the velocity and acceleration or the water particle kinematics will not vary much. So, for all practical purposes, the member can be idealized as a single line member along its axis. If the member is large, it means if the diameter of the member is much greater than 0.2 of its wavelength, then the point where you measure the water particle kinematics will matter. Okay. So that is the advantage, or that is the difference in case of slender structures in computing the wave forces or hydrodynamic forces, if this is satisfied. In such case these two are idealized as a single inertia term. Now the question comes, how will I include the relative velocity term which is acting because, or which is happening because of the pressure effects caused by the movement between the water particle and the structural member. So when the structure is present or interferes with the wave field, under the action of waves, the structure will vibrate. So this vibration will cause waves to radiate away from the member. This radiated waves will result in reaction forces this will be set up in the wave field, and this will be proportional to acceleration and velocity of the structure. So the reaction forces generated because of the radiating action of the waves from the member is proportional to acceleration and velocity. Now the reaction force proportional to acceleration of the structure will result in added mass. Or inertia effect. The reaction force proportional to velocity of the structure will result in what we call potential damping force. In such cases, the velocity term will be replaced by relative velocity. So therefore, the drag force will be calculated based on the relative velocity between the water particle and the structure. Now, the total force acting normal to the member, I should say to the axis of the member, can be given by N stands for the normal, so as per the sequence this becomes equation number 10. So, I rewrite this because I got Cm rho dV. I will explain what are these terms slightly later. Let me rewrite this. This amounts to equation number 11, where rho is the density of the fluid, CD drag coefficient, Cm inertia coefficient, Vn An velocity and acceleration of the water particle, Xn x dot x double dot velocity acceleration of the structure, dA exposed area, dV displaced volume of water per unit length. So, this will give me the total force acting on the member, which is accounted for the relative movement between the structure and the water particle. This equation, that is equation number 11, has some critical points. 1. This equation is valid only when x dot is phenomenally high. So, for having the structural acceleration or the velocity to be very high, the structure should be flexible, okay. Otherwise it will not. If it is a rigid structure or it is a stiff structure, then the velocity of the structure is x dot is the velocity of the structure will be low. This equation has got a critical issue, that is valid only when the x dot is relatively high. The relative velocity term produces both acceleration excitation and damping force. It has got both the components, okay. It has got both the components. Vn will give you the excitation force and x dot n will give you the damping force of the structure. So, depending upon the value of these two, they may get cancelled and so on. So, this has got to be handled very carefully in the design. The third component in this equation is estimation of CD and CM. That is the drag and inertia coefficients. So, there are intensive research happened reported in the literature of estimating the drag and inertia coefficient depending upon the Reynolds number and Killigan-Carpenter numbers. I urge you to refer to the respective literature to find out this, but for our information, CD generally varies from 0.6 to 1.2 and CM varies from 1.2 to 2.0 relatively. Now, in case of large diameter members, that is when D is very large, then the incident wave is disturbed by the presence of the structure. In such cases, the viscous forces become less significant. This is because the ratio of wave height to diameter, that is h by d will be very small. The diameter is very large compared to the wave height, therefore the viscous force becomes less significant in your calculation. In such cases, detailed numerical studies are required to compute the forces. The next aspect, as I told you in the beginning of the lecture, is that hydrodynamic forces has got essentially three components. One is the spatial dependence, other is the time dependence, the third one is wave direction or what we call as phase lag. Now let us see what is the effect of phase lag on the force estimation. We will take an example and see what happens to the phase lag. In the last lectures, we discussed about different geometric forms of offshore platforms or marine structures. Let us, for example, pick up a case where I am talking about a TLP. The plan of a TLP, as we all know, is the plan of a TLP. We have got column members, we have got pontoons, and the column members generally of a diameter 12 to 16 meters and the pontoon members of diameter 12 to 14 meters. Since the platform is actually designed to satisfy certain functional requirements like production drilling, storage, initial processing, etc., it requires a very large plane area. A typical size of a TLP in the literature, if you see, the center to center can be as high as 90 meters. Let us look at the sea state where the wave periods can range from, let us say, 6 seconds to 12 seconds or worst by worst 15 seconds. Let us pick up a wave period of 10 seconds. Wavelength approximately is 1.56 t square approximately for a deep water condition. If we apply this, this becomes 156 meters. Now the phase angle theta can be given by a simple equation two pi delta x by lambda, which I say in my case approximately 1.2 pi. Okay. So, there is a multiplier to pi which makes an alternate or a reversing effect on the member. Okay. This is what we call as the phase lag difference. So, this phase lag difference or phase lag effect can cause global forces in addition to the actual forces. Now, interestingly, I can fix up the phase lag for the member so that the forces can get cancelled. One can fix the phase lag such that the forces can get cancelled. So, let us take the same example. In this case, the delta x, which is the spacing of the column, is chosen in such a manner that wave forces because of phase lag gets cancelled. So, this becomes essentially a design problem. So, you will select the dominant wave period in a given C state. For that wave period in a given C state for the water depth, you can select the spatial difference of the member which will attract the wave forces in such a manner that the force on member 1 and member 3, for example, will get cancelled. So, that will cause net reduction of force on the structure. Is it clear? The other important aspect is the damping force. The first of its kind comes from the structural damping, which is generally taken as .2 to 0.5% of the critical. There is a very interesting reference for this. This is true when you use steel platforms. For concrete it is different because it is a material damping actually. So the first aspect is structural damping, which is around 0.2 to 0.5% of the critical if it is steel. The subsequent aspect will be the aerodynamic damping, which comes from different sources, which we will address in the successive lectures. So once I complete aerodynamic forces, I will talk about the wind forces, we will talk about the ice loading, we will talk about the earthquake loading, and then tidal currents. So we will try to give you a summary what are the different kinds of forces acting on the advanced marine structures. Once we understand this, we will talk about the ultimate load design and the factor of safety in the design. Then we speak about the plastic analysis and design of marine structures. Then we apply this to different kinds of structural members, including the joints, and study the failure phenomena for the joints in the first module, which will have about 20 lectures. Now we have finished today the 6th lecture on this.